guess what today is? It's another Tuesday on IAEI News Live. My name is Thomas Dimitrovich, and we're talking risk today. So today, let's focus on risk, and it all starts now. All right, so here's the thought process. Welcome to another Electrical Safety Month. Today it's May. Nihad. Hey, yes, we are live again, Nihad. Thanks for joining in. And we're going to talk about basically risk, and I think Nihad, very similar to our discussion at, where was it? I think we did it in Africa, for Power Africa, if I'm not mistaken. So a very similar discussion in that regard. So I basically want to talk a little bit about the elements of risk and I think talk about, hey, Brian Rock. Well, you know what, Brian? Even a blind squirrel gets a nut every now and then. All right, so so I thought, remember that this month, if you did or did not know, Jody Wages, thanks for joining, Mr. Joseph Wages. So if you did not know, May is Electrical Safety Month. So this is a month that we set aside, and if you go to esfi.org, hold on, esfi.org is the Electrical Safety Foundation. Put this up there. And I'm going to see if I can get this to work. Boom. So May is Electrical Safety Month. National Electrical Safety Month. Each May, ESFI commemorates National Electrical Safety Month to raise awareness about critical electrical safety topics. So this will give you a little bit of the background on Electrical Safety Month, and I'll let you take a look at that. But what I wanted to focus on today was a discussion, or is a discussion around risk. Now, NFPA 70E tells us that risk is comprised of two key components. One is likelihood and the other is severity. So risk is a combination of the likelihood of occurrence of an injury or damage to your health and the severity. Now, we try to eliminate risk, but I would argue we are basically managing risk in general. I can say from an electrical perspective, I can eliminate the shock hazard, I can eliminate an arc flash hazard, but from safety perspective, I may not be able to eliminate the fall. I may not be able to eliminate cuts and abrasions and everything else. So safety, just thinking about the word safety, is more encompassing than just electrical safety. I think it's an important thing to remember that if you have a contracting business, if you just think in general, just personally, we accept risk, we expose ourselves to risk, no matter what, walking up and down the steps, going outside to get the mail, getting in a car driving to work, getting in an airplane. Everything we do carries risk. Likelihood may be low. Hey, Alfredo Suarez, thank you for being a part of the forum. Please let us know where you're from. So we all accept some level of risk. It's the likelihood and severity. Likelihood of the occurrence and the severity of injury or damage to health. We can measure severity. Engineers, contractors, we know how to quantify, how to picturize, or put an image to severity. I can give you a video to show you severity. Likelihood, a little bit different. Miami, Florida. Well, Alfredo, hopefully it is warmer in Miami than it is here in West Bygod, Virginia. So thanks for joining from Miami, Florida, brother. So Brian says, to eliminate the risk, there are at least two elements. Continue, Brian, please. Now, let's talk about likelihood. Likelihood is typically a discussion around probability. And I'll pepper in there, this probability with personal opinion, right? Whether or not something is going to happen doesn't necessarily come from a statistic. We, as human beings, will pepper in our own personal experiences, right? So we could sit down and say the likelihood of falling down the steps when I come down in the morning. When I come to work in the morning, I go down in my basement. My wife says, have a safe trip to work. And I go down the steps. But there is a likelihood that I could fall down the steps. I could sit down and say, you know, based on my experience, I've been up and down those steps for I don't know how long. I've never fallen down the steps. So I could say it's very not likely at all. And I basically take my experience and I generalize it for everybody. Not recognizing that someone else may say, I've fallen down steps many times for whatever reason. They might have a dizzy issue, they might have whatever, or just bad luck. We tend to have our personal opinions influence, and we'll take what our personal opinion is and then say, well, it's the same for everybody. So that's where statistics help us understand likelihood. Terry Richardson, good afternoon. Dwayne Herb, it helps to have safety meetings every day before work. Absolutely, Dwayne. And the key thing is you're raising awareness. You're putting likelihood and severity. When you have safety meetings, we are trying to control likelihood. Thought process is if before I come down the steps in the morning, if my wife says, hey, be careful going down those steps, they're dangerous. I might make decisions that impact whether or not I fall because I'm now aware. I'm addressing likelihood. I haven't addressed severity. If I accidentally trip and fall down those steps, severity is going to be the same regardless of whether or not I turned the light on or turned the light off. I looked at the first step before making the step or I didn't. Severity is going to be the same. And yes, Jody, it depends on how many adult beverages we had before we went down those stairs. But the severity, Some people would argue that severity might be less, actually, because anyway. Okay, so Brian says, duty to warn, which in turn consists of clarity of warning, identifying what the risk is, what remedial steps, and persistence of warning, permanency. So when we say we're going to manage risk, I can manage risk by managing likelihood or severity. Now, how do I determine likelihood? I can look at past incidents, and what do? Brian knows this well. He used to be on panel 2. And anybody involved with the code process, Consumer Product Safety Commission gives us statistics, right? So the CPSC, whoa, the CPSC, let me see if I have, there we go. Let's do this. If I search for CPSC shock statistics, electrocutions, look at this. There's injury statistics. I can go all the ways back. I got electrocution report from 2004 to 2013. Let's take a look at that. It's a PDF produced by the Consumer Product Safety Commission, United States of America. It tells us estimated average of 48 electrocution fatalities associated with consumer products over a 4-year period. Standardized age, the victim age appears to be a factor of electrocution. During the period covered by the report, there were more than 3 times as many electrocutions to victims 40 through 59. More than 9 times as many estimated consumer product-related electrocutions to males than females. So this helps. What this does is this puts us in buckets. I mean, you do this in doctors. I mean, if you go to a doctor and you ask the doctor, if the doctor says, hey, you have this condition, and you go, oh my goodness, well, what are my chances of survivability? And they might say, well, depending upon your age, because you're in this age bracket, because you're in this weight class, because you're of this ethnic origin, they may be able to tell you what your chances are, right? And how do they know that? They know that from statistics like this. We're doing the same thing here. Hold on. Let's look at the data. They've got estimates of electrocutions associated with consumer products. Here's the electrocution records from NCHS, the electrocution records from the CPSC, the estimated CPSC in-scope records, staff national estimates, and then the percentage, right? All the ways through over the scope of this report. So the CPSC has a lot of data available, and these are statistics that help us use, that help us estimate likelihood. We can use industry benchmarks as well, right? Lost the streaming. Duty to warn. Don Gannier, Brian Rock, too bad CMP7 does not understand the remedial steps. Signage requirements in 555.10. Hey, Felix Sandoval. Good to have you here, Brian. Excellent. All right, so severity is a discussion around how bad or how serious the injuries are, right? So if I look at a case like this, if I look at a stepladder, for example, you might say, well, what's the worst that could happen? You maybe bruise, maybe you get a bruise. But again, the severity of a fall from this point depends on how you land. The impact or the severity may depend on how old you are or how young you are. The severity might be dictated by a lot of different things. So, could somebody be killed falling from a ladder like this, I would never say it would never happen because there's too many variables. Whether or not you can die falling from a ladder at that height is a discussion of likelihood. And what are the impacts to likelihood? Likelihood may change based upon your age, may change upon what the surrounding area is like. For example, in this case here, we've got a cement pad. If you have stones and rocks, could you hit your head? Likelihood may depend upon what type of personal protection is being worn by this individual. Obviously, there's no harness involved, but if they have a hard hat on, do they have other protective measures that they're taking with regard to the personal protective equipment? So likelihood and severity may be different depending upon who is standing on that ladder. Jumping out of a perfectly good airplane, right? That depends. Likelihood and severity. How do we control likelihood? We do training. We get education. We take a class on how to safely jump out. In this case, they've got the buddy pass going on. So you have one individual who is controlling the jump, who is controlling the chute, and you can see all the protective harnesses that are in place. Now, whether or not the chute opens is a likelihood thing. And how we manage the likelihood of the opening of that chute is how it was packed. Who packed it? Were they qualified? All those good things come into play when we think about likelihood and severity. And obviously, severity, regardless of the reasons why, if they don't deploy a chute, severity is the same. Hey, Brian, watching on the big screen. Excellent. Thanks for joining. There's likelihood and severity with regard to driving in a vehicle. There are statistics. So let's talk about that. Let's talk about statistics. Driving accidents, right? Wow, look at this. So if I just do a quick search for population fatal motor vehicle crashes, motor vehicle crash deaths, and motor vehicle crash death rates. This is based upon the state-by-state IIHS. Let's just go to that website. What is IIHS? Let's do a quick, what is this? Who is IIHS? Who we are? Oh, Insurance Institute for Highway Safety and the Highway Loss Data Institute. So here's another resource, right? So look at this. This tells you the population, tells you the vehicle miles traveled, the number of fatal crashes, the number of deaths, the deaths per 100,000 population, and the deaths per 100 million vehicle miles traveled. And they've got it by state. Let's take a look at where West Virginia is, because that's where I'm at. Vehicle miles traveled are 16,000, or is that? No, that's millions. So it's 16 billion, 79 million miles traveled. Population is 1.7 or 1.8 million. 257 fatal crashes, 280 deaths. Deaths per 100,000 population is 15.7. Wyoming is up there at 19, but they have less population. Texas, look at Texas. Texas is up there at 15. Oh, wait, we had somebody from Miami, Florida. Where's Florida? Florida. Let's see what Florida says. 21 million people, almost 22 million people in Florida. 217 billion, 566 million miles driven, 3,451 fatal crashes, almost 3,800 deaths, 17.1 deaths per 100,000 population. So we have statistics. We have crash types. Look at this. We have alcohol involvement. Jody Way, Joseph, you mentioned the adult beverage, right? So there's your adult beverage restraint use. How many of them have had restraints? Which ones didn't? And then rural versus urban. So my point here is, when it comes to these different methods, or not methods, but when it comes to risk based upon whether or not you are driving, flying in a plane, jumping out of plane, whatever it is, or electrical shock, arc flash, falls, trips, all of those things, we have statistics to help us understand likelihood. And then we have to all understand we accept some level of risk. If you ride a motorcycle, you're accepting some level of risk. If you drive a car, obviously you're accepting some level of risk. No matter what it is we do, we accept some level of risk. Then we have to understand, from an electrical perspective, what are the possible hazards? The first hazard that we have, well, there are 4 hazards. We have basically 4 hazards. We have a shock hazard. We have an arc flash hazard. We have an arc blast hazard, and we have a thermal burn hazard. So 70E helps us understand those 4 hazards. They identify that as the 4 electrical hazards. Now, the difference between a thermal burn and an arc flash, well, an arc flash is still a burn. You would say, well, what's the difference between an arc flash burn and a thermal burn? Well, the thermal burn that we're talking about, I can get a thermal burn on a 24-volt DC circuit. All I need to do is pass that current through a piece of metal where it's not supposed to go, or even if it's a resistor. I can have a resistor. Resistors gets hot. I can have risk of a thermal burn by touching that resistor or that energized part. I may not have a shock hazard. I may not have an arc flash hazard. I may not have an arc blast hazard, but I can still have a thermal burn hazard because the temperature of what it is I'm touching, right? So, having said that, let's talk about the shock hazard. Shock hazard is when you pass current through the body that causes damage to the body. Now, you have, I say there's 3 key components when you think about severity to the human body when it comes to shock. The path that the current takes through the body makes a difference from a severity perspective. If I have current that passes through one finger and out the other finger, yes, current takes all paths through the body. So to say current only, if I said I grabbed the wire this way and current only went, I touched the conductor this way and current only went through this finger and back out that finger, that would be wrong because current through the body takes all paths. So even though I felt it through here the most, and it caused my muscles to contract, current went through all of my neurological system, all of my veins, everywhere around, through all of my body, right? You may not have felt, or it may not be evident, the impact to your neurological system and everything else in your body. Current did pass, those electrons did pass through your body. So, but the severity would be different if the current went from this hand to this hand through my chest cavity. So the path that the current takes through the body makes a difference. The magnitude of current through the body. So if I touch two different conductors from two different polarities and 1 milliamp flows through my body, is going to be less damage to my body than if 1 amp flows through my body. So the magnitude of current that passes through the human body makes a difference. So we have the path that it takes and the amount of current that passes through the body. The third piece of the puzzle is the clearing time. How much time I let that current pass through my body. A lot of people make a mistake and they think that if I'm on a GFCI, I will not get more than 6 milliamps of current to pass through my body because it trips between 4 to 6 milliamps. That is wrong. If you do the math and you say, well, based upon the math, my resistance, the resistance of the impedance of the system, 7 amps is going to flow through my body. I don't care if you're on a GFCI or ground fault protection of equipment, whatever it is, 7 amps is still going to pass through your body because the only thing a GFCI does is it stops that flow in a period of time. That's all it does, right? So keep in mind that when you're on a GFCI protected circuit, it doesn't impact the amount of current passing through your body. It only impacts the amount of time that we permit that current to flow through your body. So 3 aspects when it comes to shock: the path that the current takes through your body, the amount of current that takes through your body, that goes through your body, and the amount of time I permit that current to flow through your body. And David Engelhardt, he may be late, but he's worth the wait. I don't know about anyone else. I, for one, am looking forward to Shock Week. Yes! I can't wait. All right. Injury and damage to health resulting from shock is dependent upon the magnitude. Oh, I forgot about frequency. So this is another discussion. Okay, so this is another discussion. And I'll tell you where we run into this discussion. Frequency. All right, hold on. Let me show you something. So, I've got a document. That okay, shock. PDF. It's go to kind. I gotta go to PDF. Here we go. For high frequency shocks, I think it was Fortescue. I can't remember who it was. Hold on to your study here. NIST, OSHA, Workplace, Dalziel. Here we go. Control F. Frequency. Look at this. Now, I am in a document that was created back in, oh, look at this. D. Arsenval. You guys all probably know who D'Arsonval, or you probably know of a D'Arsonval meter. But look at this. Two items of interest. This is from the 30s, 1930 what? 1939. Two items of interest in regard to the ability to withstand high-frequency currents were noted in reviewing the data. Hooker and Lotz and Kuovenhoven, as a result of their experiments upon dogs, found the average value of current necessary to produce fibrillation at a frequency of 1,260 cycles per second was more than 12 times the value in 60 cycles. D'Arsonval, I love this. Imagine this. Imagine, oh yeah, no, I am. So imagine if you would, a time when you decided to take 3 amps of current and place it through your body at a frequency of 1 million cycles per second. From 4,000 to 1 million cycles per second. D'Arsonval could withstand as much as 3 amperes without ill effects. The twitching and everything else, we don't associate that with the shock. But this is the only data that I'm aware of where human beings, or in this case dogs, were exposed to high-frequency currents to determine the impact on their physical nature. Felix, I can get you a copy of the study. So Fortescue, Felix, C.L. Fortescue, that's right. Fortescue was the symmetrical competence. You are the man. C.L. Fortescue was symmetrical competence, was D'Arsonval who did the frequency. Very good, Felix. D'Arsonval in 1892 found that he could withstand as much as 3 amperes without ill effects at a frequency which ranged from 4,000 to 1 million cycles per second. That's a lot. So, I would not want to test that, but it just shows you that when you have a theory and you feel very sure of yourself, that's the way that goes. So frequency matters as well. And then we know, based upon data from, let's talk data. You want to talk data? Let's talk about this thing called data. Let's go back to that PDF. I like talking about this, the history here. Oh, crud. Bear with me. Because I have a problem I'm trying to solve. Oh, there we go. All right, so let's talk about this. So let's go back. I'm gonna set the stage. There was a report done in December of 1939. Electric shock as it pertains to the electric fence. This is my earliest. Outside of the 2 frequency things from the 1800s, this is the earliest that LT commander data is it. LT, I'm not sure what that means. This is the earliest data that I have in regard to shock. And what was going on, and this is what, the 4th printing, April 1955. So what was going on back then was that farmers were starting to use current around an area to keep the cattle in. So they were electrocuting kids and sometimes cattle. And so a manufacturer said, I'm going to come out with this pulsed DC solution. And Lieutenant Commander Data from Star Trek. Yes, Data! Thank you. You know who should have known that was Brian Rock. So in this case here, safety for a 2-year-old child, they were trying to figure out the safety for a 2-year-old child when exposed to contact with an electric fence. And they were coming up with a product, and they needed to come up with tests. But they have to understand, what is the impact of current on the body? So they were using typical uses of electric fence: keep pigs in, keep cattle in. Okay. So the popularity of electric fence is indicated somewhat by a statement of Professor Riley, who estimated that there were probably between 50,000 and 100,000 units in operation in 1938. So electric fences. So UL tried to come up with the data. I'm looking for, okay. The purpose of the investigation: determine the maximum value and the nature of that current which within certain limits of frequency and time of contact can be considered as not being hazardous to human life. They said it is proposed to establish that value as one which will be safe when experienced by a 2-year-old child under the conditions most favorable to the reception of electric shock. Okay, the worst conditions under which the child might contact an electric fence wire would include the following: the child barefooted, standing in a pool of water or mud, and falling across or grasping the wire with 2 wet or sweaty hands. The wire, so far as the child is aware, being an ordinary non-electrified fence. So, they know the nature, they have heart failure, all that good stuff, everything that we know. Let me just get to the right spot. Okay. Look at this. Now, if you do any 70E educational programs and things like that, you probably have recognized this. Laboratory tests have shown that human tissue as an electrical conducting medium is somewhat analogous to a circuit consisting of a high resistance in parallel with a high capacitance. So a resistor in parallel with capacitor. The chief resistance of the body in electrical current is at the point of contact with the circuit. That's where your skin is touching the circuit. Repeated tests have shown that thoroughly dry skin on the hands has a resistance of approximately 40 to 50,000 ohms per square centimeter. And it can drop as low as 1,000 ohms when the hands are wet. So this is 1939. And we have this data based upon tests. And it has a note 3, so I'd have to go to find note 3. And it says several measurements of body resistance taken during criminal electrocutions have shown that with the use of large electrodes with approximately 2,000 volts potential applied, 8 to 10 amps of current flowed through the body. And that would indicate that under those conditions, the human body has a resistance of approximately 200 ohms. So what they're trying to get to is the impedance of the skin, because that's the highest impedance. But they really want the overall impedance of the human body. For animals, keep the current value just south of roast beef. The value of body resistance hardly seems justifiable in connection with the electric fence application because it's not possible to have that large of a contact area. Remember, the contact area was body was shown that 2,000 volts, 8 to 10 amps of current. This would estimate, what was the contact area? I can't remember the contact area. I thought we just read it. But in any case, so they said that the data is good, but it doesn't necessarily apply to this application. So I'm going to find the next good piece of information. Now, they have a table where they determined the impedance of the body. They said that For the limited number of tests, there were no trends or relationships between the body resistance of individuals and their sex, age, height, or weight. So they felt it necessary to conduct the same tests on children, as the foregoing data did not indicate whether the resistance of children under the given conditions would be greater or less than recorded for adults. So the first thing they did was they tested on adults. And then they decided, hey, we're going to have to go grab some 3 to 15-year-old kids and figure out what their impedance was. So they did not want to hurt those individuals. They wanted to do the tests. Measuring the currents in the series of tests did not exceed 1 milliamp. So well below the shock threshold, 1 milliampere, and they were going to determine the impedance with a 12-volt potential. So they kept it safe. So what they learned was a study of the following tabulated data shows that the body resistance of children is higher than that of adults measuring under the same conditions. And I'll tell you, I had a problem with that. I'm sitting there thinking, how could the impedance of a small child be higher, larger than the impedance of a guy like me? It appears safe to assume, therefore, that the lowest body resistance, which might be reckoned with in connection with the electric fence application, would not be less than 500 ohms. Now, here's the thing. Why is that the case? So I was at an electrical safety workshop, and I had a discussion with a doctor who was researching current through the body. And his research was, remember earlier when I said about when you touch a conductor and the current goes through this portion of your hand, and I made a statement, it goes through all portions of your body because current takes all paths. What he was studying was these low current shocks that are persistent on electricians over a period of time have an impact on the neurological system of that electrician. And what he recognized was that there were patients who inexplicably, hey Nihad, thanks, take care buddy, we'll talk to you soon. He had some patients who inexplicably couldn't maintain balance, and he tied it to this current through the body. Now, I brought this sentence up to him, that resistance impedance of a child is greater than an adult. And you know what he said? He goes, that makes sense to me. And I said, why? He said, because in the human body, current takes all paths, right? So a larger individual will have more parallel paths for current to flow through the body. And when you have parallel paths, you have parallel resistances. When you combine those, the overall impedance is lower, not greater. A child who is smaller has less parallel paths. Now, that's a theory, but it makes sense. So here's where we get the impedance of the human body to determine the amount of current that passes through the body. And here's the data. So look at the subject, body resistance of, this is the age of the subject, the weight of the subject, hand-to-hand impedance, hand to feet, hand to dry, hand to hand wet, hand to feet wet, and then the right hand to feet wet. So these are all of the ohms in resistance for each of these individuals, whether they were male or female. And this is the impedance of children. And you'll notice that the impedance values are greater. And they went down as low as 3 years of age, 3, 4, 5, 6, 7, 8, 9. So the youngest was 3-year female, 3-year-old female. And then you had a 4-year-old female and male. And you have their heights in inches and their weights in pounds. So I'm not sure if Dr. Lee was involved with electric shock, Dawn. I don't believe so. Dr. Lee I know the Dr. Leah that I know was involved with arc flash. So, but these are those data points. These are the accident records. They had in England a fatality, circuit 65 volts at 50 cycles. In Vienna, 60 volts and 50 cycles. In Italy, 45 volts and 50 cycles. These are your laboratory tests, AC voltage milliamps. Let me get to something I want to make you dizzy. I'm spending a lot of time on shock because shock is the #1 killer. We already talked about that. So I'm looking for, here we go. Look at this. Laboratory tests. Thompson of the Electrical Testing Laboratories conducted an extensive series of tests upon a number of individuals and found that for women, the average maximum tolerable value of current was 5.15 milliamps. The corresponding value for men was found to be 8.35 milliamps. The average was 7.1 milliamps, and the maximum value recorded in the test was 20 milliamps. So in this case, they were passing more current through the human body, but think about GSCIs, 4 to 6 milliamps. That's the let-go threshold. Then Grayson reported that similar tests performed upon 42 men indicated that the average man could detect 1.2 milliamps. This is detection. Remember, there's that table about detection, right? And none could withstand a current of more than 8 milliamps without serious discomfort. And that's probably your muscle contraction. This is when we were getting to learn that above 6 milliamps, we had muscle contraction. And then R.R. Corey conducted a similar experiment, performed a test upon himself. Think about that. They tested on themselves. He found that a current of 14 milliamps caused paralysis of certain parts of his body. I mean, that is research to the nth degree. Gilbert, as a result of tests to determine the specific contact resistance of the hands, found that the average individual could not easily free himself from a circuit greater than 15 milliamps. So quite recently, I'm talking severity here. The more we understand about the hazard, the more I can help you understand the severity aspect of shock, of current passing through the body. The 6 milliamps is not defib. Look at this. I mean, this guy went through 12.6, 13.9 milliamps. It didn't kill him. Their heart didn't go into defib. Why? Because defib doesn't happen until like around 40 milliamps, 30 to 40 milliamps, somewhere in that ballpark. We just saw 15 milliamps here. So here in the United States, we care about let-go thresholds. Your body can actually take more current, but it depends upon the condition you're in, or the condition that you are aware of that you're in. You may have a condition that you're not aware of, and you could succumb to current through the body not because of it was 13.9 milliamps, but because you had a health condition. But look at this. Tests indicated that for a pathway hand-to-hand, the maximum average tolerable current for 56 men subjected to 81 tests was 13.9 milliamps. So they subjected 56 men under 81 tests with 13.9 milliamperes hand to hand, directly across the heart. So in 1855, Mohn applied electrodes directly to the human heart and found that an alternating current of 15 to 30 milliamps did not adversely affect the heart's action. Remember, we said defib is around 40 milliamps. Dixon and Mann's experiments disclosed that a current through the chest of from 15 to 30 milliamps did not upset the heart's action. Trotter found that a direct current of 35 milliamps from hand to foot was not fatal. So we have a lot of research that we rely on, but it goes back a long time based upon, I call it the sins of our fathers. We had a Dr. Lee that presented to our local from the University of Chicago. It's not the same Dr. Lee that I'm thinking of, Don. So Dr. Lee that I know is from Texas. So there was a Ralph Lee. There was a Ralph Lee, but I don't know that he was a doctor. The long-term neurological issues of electric shock. Yes, and you know what? Founded the Chicago Electrical Trauma Rehabilitation Institute. God bless that man. So I may not go into defib at these currents, but remember, here in the United States, the 4 to 6 milliamps is all about let-go threshold. It's not till you get to around 40 milliamps that you start to get to the defibrillation area, again, of a healthy person. Brian, DC, I'm not sure who you're asking, but DC does not have frequency. So when I talk about frequency, now the DC, okay, so the 35 milliamps, hold on, there's, we just went over DC current. Hold on, it said, this is 60 cycle. Hold on, I just read a DC current. Hold on. I just saw DC somewhere. I just saw DC current, Brian. I'm not sure where it was at, but I don't believe. A lot of this was done on AC, but there was in here somewhere testing that was done with DC currents, and I can't find it. I can't find it. So it could be that I'm reading it, so I'm just going too fast. But in any case, yeah, I'm not finding the DC tests. $110. So roughly the test consisted of subjecting the rats to potentials of 110, 240, 500, and 1,000 volts for periods ranging from 1 second to 1 minute. I know they did. Oh yeah, here we go. Here it is. They did testing in DC as well, Brian. Subjects 11, 33, 29. This is voltage 110 AC, 110 DC. So 10 to 48 milliamps in AC, 28 to 47 in DC. Maximum contact time 10 seconds, 20 seconds, 28 recovered, 4 died, 1 paralyzed. So here is some data. What is table 4 from? Jeez, man, how did they get that? Table 4. Where is table 4? I'm not sure what the reference is for table 4. Recovery in every case was brought about by artificial respiration. Look how many seconds, though. 20 seconds. 28 to 47 milliamps for 20 seconds. That's a long time. 220 volts DC. So the death of rats, oh, wait a second. These are rats. These are rats. All right. These are, yeah. The 110 to 120, 220 volt alternating current circuits are more dangerous to rats than the direct current circuits of the same voltage. A large rat can withstand a greater shock than a smaller rat and still survive. So these are not people. These are rats. I was like, oh my gosh, did they actually kill somebody? Now, if I was a rat lover, I'd be like, hey, you shouldn't kill rats either. Head to tail, these are all the subjects, the voltages, the ampere. So they did tests on rats as well. So there is a lot of information around shock. And I can go back to the 1800s. So the data that we use to understand severity of shock, of current passing through the body, goes back over many of years from tests that are done by researchers on themselves, tests that are not tests, but executions, tests that are done on dogs, on rats, tests that were done on children and male and female of different ages and sizes and all that stuff. So the following legend, so I'm just looking through some of the data. They've got average weight and current periods of time. I'm dropping stuff down below my desk. Minimum fibrillation. They've got charts. I'm looking for, I typically highlight stuff in here that I thought was interesting. Let me come down. Hold on. Hold on, Brian. So they did an allowable current curve. Arbitrarily decided to terminate the curve at 65 milliamps as the maximum allowable current value and the maximum allowable output, 4 milliamps. Remember the 4 to 6. It was also decided that the on period of an intermittent type controller should not exceed 0.2 seconds. This resulted in terminating the lower point of the curve at 5 milliamps. The curve determined by these points maintains a safety factor of approximately 6 between the minimum fibrillation and allowable current values. They also noted that minimum fibrillation current and allowable current is based on the fact that there are no available data on repeated shocks at less than 5 minutes. Intervals, whereas the majority of electric fences supply electric shock impulses at the rate of approximately 60 per minute. So now they're getting into the discussion of pulses, how long, and hey, Susan. All right, I'm going to keep going here because I want to get to another piece of the puzzle. I don't think I've ever shared a lot of this data with all of you. But I love this data because it really helps you understand current and the impact on the body. Okay. They did some research for the field experience. Oh, and there's the studies. So remember the references. Effects of electric shock, 1930. Electrical studies of living tissues from 1936. Electropathology in 1928. As Humane as Possible by Robert Elliott, October 15th, 1938. So I guess that means get data as humanely as possible. So these are just some of the references in this document. So my point is, throughout this entire discussion, that we have to understand risk is comprised of likelihood and severity. And The likelihood of something happening is a very human factor. The severity is something that we have a lot of data and research on for some aspects of hazards. We know how many people are hurt and killed in accidents. We know how many people are hurt and killed in falls, from shock, from arc flash, all these things. We have to base what we do in a design, we have to base what we do in the code on those aspects of likelihood and severity. And I'm going to pepper on top of that a little bit of our own personal opinion and our personal, which is developed through our personal experiences. Make sense? I hope you got something out of this session. I thank you for watching. Thank you for what you do for electrical safety. Thank you for what you do for the electrical industry. Remember to stay safe. And please stay healthy. Brian, I can get you a copy of that report. All right, everybody. Take care, stay safe, and please stay healthy. Talk to you soon.